Um, Good afternoon, everyone. This is a wonderful opportunity that I've been given. Thank you so much for the organizers and my wishes to the chair of the panel as well here. So my name is Srinath. I'm one of the co-founders of this company called Agnikul Cosmos. I think Professor here was also talking about one of our engines that we have been working on, rocket engine that we've been working on. At Agnikul, we are actually making small launch vehicles that can take small satellites to orbit on demand. That's what we are actually focusing on. So, in our experience of doing this, we to make rockets or launch vehicles quickly. We went through the process of 3D printing a rocket engine, and that taught us a little bit of materials, a little bit of 3D printing as well. So I'll cover both of that. I know there's a separate session on 3D printing as well, but here our experience on iterating through various materials that are used for rocket engines is what I wanted to quickly talk about. Here is the agenda itself. I'll quickly skip. And about the company itself, just so that you give more context, right? So we are working on a vehicle that can take up to 100 kgs or even at the higher scale up to 300 kgs to low Earth orbit, with the core focus on customizing the vehicle to the customer, as opposed to saying, hey, here is a vehicle, then you can just fly that if you're able to fit into that. Can we actually modify that whole process and actually make it like if there is a customer, you can actually tweak the vehicle to address the customer, so that the pricing and all that is not like a one size fits all configuration, but you tailor it to the customer. So in this, the two engines that we have, the first stage and the second, it's a two-stage vehicle. The two engines that we have are completely 3D printed with Inconel. So just wanted to talk about that. This is the scale model of the full-scale vehicle. We had the opportunity to present it to our Honorable Prime Minister during the inauguration of this new entity under the Department of Space called InSpace, which is fairing the entire space ecosystem today. And this mission here, the what we call as the Agniban Sorted. So Agniban is the name of a full vehicle. Sorted is short form for the suborbital tech demonstrator. We hope to fly it hopefully early part of next month. We have one more test pending, and we work out of the ID Madras ecosystem. There's one more test pending. If that goes through well, then I think we can target a December launch. Hoping for having all of your wishes for that one. It'll be a vertical ascent flight, and then instead of a sounding rocket, it actually goes up. And that's a pitch over maneuver over the ocean goes there. This would be powered by that Agnilet engine that sir was also talking about here. So I think the 3D printing process itself, I'll skip these parts quickly, right? I think the whole process of where 3D printing and materials research comes together is, I think, in one line I can summarize this slide, right? In our understanding, 3D printing allows us to iterate on hardware almost at the speed of iterating software. When people usually look at hardware iterations, we talk about months, but you can get that down to a few weeks if you actually do this right here. One second. Yeah. So from aerospace standpoint itself, I think why 3D printing and materials in that aspect work really well is because there is one big disadvantage, I would say, shortcoming to 3D printing, right? Which is that speed is an issue. If you're looking at a million parts or a million components, I don't think anyone would actually, at least today, look at 3D printing as a viable approach to manufacturing. But if you're looking at only one or two components, which is purely in the R&D phase, that is also too much to invest in from a 3D printing standpoint, because the initial upfront investment is very high if you look at machines that are working well today. So aerospace sort of fits right in the middle. You're not looking at millions. You're also not looking at one or two. You're actually going commercial, and that's where 3D printing works very well for aerospace. Of course, the fact that mass reduction is always needed. Very complex geometries for your components may be there, and so on as well. So that is what that is why this comes in here. Now, I think in the previous talks as well, we spoke about nickel-based alloys, right? And those are actually very well studied, or at least people are very well aware of the problems. A lot of things have to be solved, but there at least people are well aware of the problems. But we started off initially on a journey on trying to 3D print copper. And that was actually a very interesting challenge to take up, because the very reason that copper is favorable for, say, rocket engines, for example, is the same reason why it makes it a little difficult to 3D print. Mainly because it's a very, very good conductor of heat, and you're barely able to control where the heat goes. At a qualitative level, when you're looking at, say, using like a laser beam to do welding on a particular layer through this powder bed fusion method, for example, right? controlling where you want the temperature to go up itself is a challenge. So getting precision, getting required accuracy, and particularly as geometry of the parts also start changing with height, for example. For layers where you're only dwelling for lesser time compared to a longer time and so on, it gets very challenging to use copper. But we went through this process here, and interestingly, now we have actually switched to Inconel. Our engines have been working with Inconel only, and I think we're going ahead with that for at least these two engines for the first few flights that we have. Copper continues to be an attractive option, which is why I just wanted to talk about that here. Right, I'll skip these parts here. So from a 3D printing standpoint for copper itself, I think two things, as I told you about already, the thermal conductivity part is an issue. I also think that there are other questions about first of all, even trying to model how this would work when you're going through a 3D printing process is challenging itself. There are other issues in terms of how much time you should allow it to cool and so on. So a very complex process from a 3D printing standpoint. Interesting aspect also is that the people have figured out. I wouldn't say that today it's not possible to 3D print copper. The parts don't come out well. There was an image that I had in the previous slide, for example, right? Badly printed part can look very bad and very poor, very rough and very coarse. But people have figured out what could be done. I think there are some interesting papers out there that I just wanted to bring to your attention. One is on understanding how to actually model the process of how the heat transfer happens when you're using copper for 3D printing. I think that is one, and then I think process parameters, and that is very machine dependent as well. I think that would definitely be a tweaking parameter, an experimental parameter to understand when you're doing 3D printing. Other than that, I think from the whole aspect of what levels of pressures you're having and what other post processing techniques you're using will also allow to actually have copper as a way to compete with smart alloys. I think the copper zirconium alloys are something that many commercial 3D printing machine manufacturers actually give us today, and pure copper as well is something that people are working on today, which will obviously be very ideal for very high temperature applications. The interesting thing about rocket engines, as opposed to say, for example, gas turbine engines, is we're looking even with reusability, right? Even if you actually want to bring back and use the engine over and over again, you're barely looking at a few hours of usage. Not like thousands of hours, and definitely not thousands of cycles. It's probably tens of cycles for 1 or 2 hours at max. So this is including everything in the testing phase as well. So I think in an area like that, where probably you can get over, or you can look over parameters like creep, for example, which come in over only when you're looking at hundreds of hours of usage, it gives you a sweet spot to work on. In some sense, it may almost not work for certain class of engines, but it could be made to work for rocket engines. So that is some of the studies that we're working on at Agnikul itself. So just wanted to talk about this Agnikul engine and wrap up, right? So I think with the help of the team at in Agnikul and with the support of professors at IIT Madras also, we have developed what we call as a single piece rocket engine. What you're seeing here is an image of that, a small size subscale image of that. By single piece, what we mean is every aspect of a rocket engine, right, where the fuel comes in, for example, the cooling channels, the combustion chamber, the nozzle, the igniter, which actually ignites the rocket engine, all of that is 3D printed in a single shot. So you start the 3D printing process. Of course, you have someone monitoring it, but no direct intervention of a human in the process. And what comes out of it is a fully made rocket engine. Then you can directly go for depowdering, post processing, the heat treatment aspects, and then start looking at machining to allow fuel to go in and so on, and you have a fully printed engine. So this takes about 72 hours to actually go through the core printing process itself, and after that about 8 to 10 days to go through the rest of the cycles. And I think at that point we were able to actually successfully get an engine. As with most testing applications, testing is the harder challenge than actually making the engine itself. Just wanted to play a quick video of the qualification test that we did, where we had the opportunity to invite ISRO scientists as well to come to our facilities. We have one testing facility within the satellite campus of IIT Madras, where we were able to actually do a 107-second burn of this engine. So let me just show that, and with that I can wrap up my talk as well. So obviously it's 108 seconds, I'm not playing that, but just wanted to show you that It's a 6 kilonewton engine. This is what is actually on the second stage of a vehicle as well. This is the engine, and this is basically running kerosene and liquid oxygen together. So you can see the engine has been chilled here, and you can see the frost coming. And so we were able to achieve this sustainably. The temperature stabilized around 20 seconds or so, and it's a regeneratively cooled engine. What we mean by that is, the fuel itself is actually the coolant here, and we have been able to manage this with Inconel 718 itself. And very similar, test of the same engine, but in the vertical orientation. Because the vertical orientation with the exact plumbing lines as how it would look in the vehicle itself is what is needed for final qualification. That has also been done. So we continue to believe that we understand how to use Inconel 718 for rocket engines of this class. I think maybe with copper we'll be able to push our boundaries a little more as well. But that is for the next steps of product development. So that is what I wanted to share today. Thank you very much for inviting me again, and I think this industry has a lot of promise for all of us to build on. Thank you very much, sir.
Okay, thank you, all the panelists.